This white flower here is called meadowsweet. It's a pretty common plant here in Sweden. It grows along roads pretty much all throughout the country. A lot of people probably consider it a weed, but also what a lot of people don't know is that it has an extremely interesting and important chemical story.
The story starts with this molecule, salicylic acid, a substance that has long been used for its pain-relieving properties. Salicylic acid is derived from the metabolism of a compound called salicin, which is found naturally in, for example, willow tree bark and in our meadowsweet. This has been known for centuries, and the bark from willow trees has often been used to treat pain and fever. But there were some side effects. Salicylic acid can also cause digestive issues such as gastric irritation, vomiting, and even worse if consumed in high doses, which made the medicinal effects limited. In the late 1800s, a German scientist called Felix Hoffmann decided to try and find a way to get rid of the negative side effects to help his sick father. He used salicylic acid extracted from meadowsweet and replaced one of the hydrogens in the molecule with a so-called acetyl group. It worked. By making this small modification, he improved the effectiveness of the medicine. The new medicinal drug was named aspirin, from the former scientific name of meadowsweet, Spirea ulmaria, and A from the acetyl group that solved the problem with the negative side effects. Today, aspirin is one of the most sold pharmaceuticals in the world.
It may sound strange that we can just replace a part of a molecule like this, but this is fundamental in chemical research in order to create new molecules with desired properties. But in order to make such changes, we need to first understand how the chemical bonds that hold molecules together work.
In a molecular model, the chemical bonds usually look like this, but in reality it is quite different. Chemical bonds are in fact the result of electrons being moved and shared between atoms. But there are a few different ways chemical bonds can form.
First, ionic bonds.
One example of a substance held together by ionic bonds is regular table salt. In general, elements prefer to have filled electron shells. To achieve this, the elements can either give off or receive electrons from other elements. The result is that the atom becomes either positively or negatively charged. These so-called ions can then bind to other ions of opposite charge.
Atoms can also bond to each other by sharing the same electrons. This is called a covalent bond.
The simplest example is hydrogen gas, where the two hydrogen atoms share both available electrons and therefore fill their first electron shell. But the different elements in a molecule can have different abilities to pull electrons to them. Take water, for example. The electrons move around both the hydrogen atoms and the oxygen atom, but the oxygen atom attracts the electrons more strongly, so the electron ends up being pulled to the oxygen atom more than the hydrogens. This makes the whole molecule polar, meaning that we get a slight difference in charge between the ends of the molecule. And similar polarity can be found in other molecules held together with covalent bonds.
These polar molecules can in turn form electrostatic forces and generate weak bonds between molecules. And then we have the metals, which often have some special properties. Metals can form a special type of bond, simply referred to as a metal bond, in which electrons can move freely around the atoms and form almost like an electron cloud around the positively charged metal ions.
And even within larger molecules, certain combinations of atoms can form especially strong groups together, just like in our example with meadowsweet. With this knowledge, we can experiment with how to break specific chemical bonds in order to replace certain parts of a molecule with something else, just like Felix Hoffmann did to create aspirin. And this is still what today's pharmaceutical research is all about.
Vi på AstraZeneca utvecklar läkemedel, framtidens läkemedel för att bota och behandla sjukdomar som folk lider av idag. Så vi utvecklar små molekyler, stora molekyler som ska ha en biologisk effekt.
Man kan ju sätta ihop molekyler på jättemånga olika sätt. De ska kunna ta sig till rätt plats i kroppen, de ska inte utsöndras för fort och de får inte ha för många biverkningar. För att göra det här så har AstraZeneca tillgång till miljontals föreningar i ett jättestort substansbibliotek som finns.
Molekyler man börjar med är ju nästan alltid ganska långt ifrån det man slutar med som ett läkemedel. Även om man har en effekt av en molekyl som man har hittat i till exempel naturen, så har man ofta en massa andra effekter också som man vill rätta till. Den kan ha negativa effekter i kroppen, men den kan också ha saker som kanske har en kort halveringstid i kroppen. Den bryts ner jättefort i kroppen och då måste man hindra den nedbrytningen för att den ska kunna ha effekt över en längre tid. Ja, det som gör jobbet verkligen kul, det är väl att kunna påverka dessa mest grundläggande byggstenarna som hela världen är uppbyggd av. Och att kunna modellera dem och bygga dem precis så som man vill ha det, så som ingen någonsin har gjort det innan. Och från den här molekylen få en effekt, antingen i kroppen eller i samhället som något form av material kanske.
An understanding of the chemical forces that hold molecules together and the ability to break specific bonds and replace selected parts with others can literally save lives. The research that happens here at AstraZeneca is very advanced, but with today's technologies, we can accomplish so much more than people could probably ever imagine at the time aspirin was first developed.
And just like the meadowsweet and the willow tree that we started with, we still find a lot of medicinal substances here in nature that start a whole chain of experiments in the search for the future medicinal drugs. So thanks everyone for watching today.